Good morning. It is the video lecture, the physics video lecture, the psci 168 video lecture 13. Tons of great material for you today. Let's see where we're going to get started. I didn't bring a lot of demos, don't need them. So what we have to do first is a little bit of review. Review orbit, just because it's such a great topic. Then Newton's law, in particular what the weight is. That's about as far as we got last time, okay? And then from there we're going to move on to work and kinetic energy. We needed the mass, which is what we discovered here last time, in order to discuss what we're going to discuss today is the kinetic energy. And once we know about that, I'm going to talk about asteroid collisions, an asteroid bombarding the Earth. So then I'll write work and kinetic energy. Actually, we'll say power here as well. And then asteroid. Boom, with an exclamation point. Good. So let's have a start at this. As far as the review goes, I want to just reiterate everything we learned about the orbit very quickly, because I want you to be able to do this, and we're doing our exams at home, but I'll throw some kind of thing into there to make you think of it. So suppose we want to do an orbit, a near-Earth orbit around our Earth. Okay, there's the radius of our Earth. Near-Earth orbit means that we're pretty darn close to the surface of Earth compared to the radius of Earth itself. After all, say 200 kilometers versus 6,000 kilometers. That really is just a little increment that I've drawn there. And what that means is the law of free fall is operating on our satellites. The same law of free fall we have in this room here at the surface of Earth is operating a couple hundred miles up. So that means the satellite orbit problem really turns into a horizontal throw problem. And we had L, we had a little h here, radius again. I can ditch the subscript because this same argument would work for the moon too. You'd have a different radius, a different g. But we use the Pythagorean theorem, r squared plus L squared equals r plus h, the quantity squared. You want to be able to do these steps yourself. And we found out that L was approximately equal to 2 times R times H. And this L was the distance forward in the same time that something fell that little distance H. And for R equals 6.38 times 10 to the 6 meters, that's our radius of our Earth. And h equals 4.9 meters, that's the fall in 1 second. We had V equals L over T, where T is 1 second, 7,900 meters per second roughly. So that's the orbital speeds. I think I assigned a couple of other things for us to deal with as well. And yeah, it's just based on the horizontal throw, the independence of vertical and horizontal motions, the law of free fall. And there you have it. So we're going to make use of this number later on. We'll approximate it by something. Okay. Good, so that was the satellite orbits, and there's so much more to say about them. I encourage you to look them up. I described a couple of different types. This was for the near Earth orbit, or generally near to to whatever body it is you're orbiting. There are others as well. Good. The next thing we talked about was Newton's law. And the key point to be made here is that force equals mass times acceleration. I'm going to go ahead and write it out again. It ties together a bunch of things that we've learned about. We've learned about forces, okay? The weights, newtons, 10 newtons, this guy right here. We've learned about acceleration, namely the acceleration due to free fall. We know about that one. So the mass was actually a new thing. This not only is a force, a weight, but it's actually an object that says 1 kilogram on it. It's actually 1 kilogram of metal, pretty dense metal, okay? 1 kilogram. And that's what this mass is. So the units here, newtons equals kilograms meters per second squared. Mass times acceleration, so those are the units. And in particular, we learned that weight is m times g. So weight is equal to mass times the acceleration due to gravity. And don't mix up these m's here. Here it's a mass, here it's a meter. You just have to recognize what it is you're dealing with. So weight is mass times the acceleration due to gravity. And that's where we're going to pick up now. We talked about weight again. We want to bring it into contact with work. So here's what we're going to imagine. We lift, well, here's a ramp with a little ledge on the end, okay? Ramp with a little ledge on the end. We're going to roll a ball up. I must have had that bowling ball in here before, I think, but I don't have it with me now. So we're going to roll the ball up and set it up here on the ledge, and we have a height h here of this ramp, and this is the ground level. Now we know the law of free fall. The law of free fall the kinematic equations, in particular, it gives us this expression here. V squared equals V0 squared minus 2g x minus x0. Okay. This was the kinematic equation that relates, and let me go ahead and write this out. This comes from x equals x0 plus v0t minus half gt squared. That's the law of free fall. V equals v0 minus gt. That's the velocity. So you took these two equations, plugged them into each other. I mentioned it. I don't know if I actually did it. You're welcome to try that. You plug one into the other, eliminate the t. You're going to get this equation here. Okay. So this relates the speed that something has and the distance it has fallen. Okay. Okay. So let's go ahead and construct what I'm construct this thing right here. So we're going to drop this object from here. It's going to pick up speed and it's going to strike the ground. V when it strikes the ground. Okay. So the speed when it strikes the ground we can get out of this thing here. We're going to get v squared is equal to minus 2g, and the x minus x0 is going to be a minus h, because it fell down. Okay, we didn't lift it up, it fell down. So the minus signs cancel. That's 2gh, and I'm going to divide, and we're going to have v squared divided by 2. And you know what? Leave a big space in here, equals g times h. Because what we're going to do is multiply. This is just kinematics. This is just the law of free fall, what tells us what happens when you drop something. Put a mass in front of both of these, m times and m times, okay? And then I want to keep working underneath here, so I can label these expressions. Okay, so I just did kinematics and multiplied both sides by m. I can do that, right? Multiplied both sides of the equation, that same thing. But look at what we have here. This m times g, that is the weight. We just discovered that's the weight, and we know the weight times the distance lifted or dropped is work. Okay. So this is weight times height is work, this entire expression, because we now discovered that the weight is m times g, this is work. And what do we have on the other side? This m v squared divided by 2 is defined as, I'm just going to write defined because we haven't seen it before yet, defined, or definition, kinetic energy. Remember we said work is the capacity, energy is capacity to do work. We call this thing the kinetic energy, KE. So it's a really simple process. You know, we worked to roll it up the hill, and we know the same amount of work whether we rolled it up the incline or just lifted it. Same amount of work, and that work is mgh. But the law of free fall tells us that when that thing hits the ground, it has this much kinetic energy. Now, can kinetic energy do work? And I've answered that before, but I'm just going to demonstrate again. If this is my bowling ball or my mass that I'm dropping, and this is a nail, I can drop it on this nail and it will punch it into a board, okay? And that's work, okay? So kinetic energy can do work or can be turned into work. So this kinetic energy is the right definition. It has the capacity to do work. And this is the simplest, or a very simple version of the work energy theorem. Okay. So I'll write that underneath here. Work hyphen kinetic energy theorem. That you can turn work into kinetic energy, you can turn kinetic energy back into work. You can do work with the kinetic energy. And the units here are the same as the units here, okay, because we just multiplied both sides by m. So the units here were force times distance is joules, and here we have mass times velocity squared has the units of joules as well. Has to, okay? So we have joules here in kinetic energy and joules here in work. So yeah, this example, I can't overstate its importance. It's just dropping something, and there's just a bunch of, since there was work required to lift it, there's kinetic energy as it picks up speed as it goes down. And the higher you drop it from, the more kinetic energy it has. Okay. So, work and kinetic energy. Now I want to discuss power. This kinetic energy, this is the missing link, and you couldn't understand it until you had Newton's law and the concept of mass. So we needed the mass. Just to write this out, mass times acceleration. And I'll just write acceleration's gravity. Good. Okay, we're going to do a number of things with this. We have a big chapter on hydropower coming up, but I have such a nice detour here, and we want to review the concept of power, which I just erased. So we start this list again. We have force, we have work and energy. So here's the Newton, here's the joule. We now also have kinetic energy. We'll go ahead and abbreviate it. KE is always a half mass speed squared. But they have the same units. They have the units of joules. But then there was the concept of power. Power was work divided by time, or energy divided by time. Okay, but we're using the word work and energy interchangeably as we need them. Okay, so power, work divided by work per unit time. P is equal to the units here, joules per second, and that's the watt. And since we have so many W's going on, I often just write the word watts out. Okay, so there's work divided by time, so there's this concept of power as well. And so in the same time that this mass is driving my stake into the ground, or whatever the work is being done, it's happening in a certain amount of time, so there's power released during that work. Okay. And remember, we had the power of the grandfather clock. That was very tiny. We had the power of us running up the stairs. That was a bit bigger. And, we had conceivably much more power, enormous values of power. So we've actually already calculated a bit of that. So you may want to review what we've learned about power in your notes. So I want to bring the kinetic energy into the power now. So now we want an example of kinetic energy and power. That's our next topic. And I'm going with this collision. This thing drops down, doesn't work. There's also power released. But we're going to immediately do a very large example, namely an asteroid collision. And when I mean asteroid collision, I mean an asteroid that collides with our Earth. Okay? Not just out there in space somewhere. Asteroid collides with our Earth. Okay, so I'm going to set that up. See how we're doing time-wise here. Fantastic. Good, so our next topic is the asteroid collision, and it's going to use everything we've learned. So let's go ahead and draw some of this here. This we can get rid of. We have everything. So there is, in Arizona, there's a thing called the Arizona Meteor Crater. I'm going to make that part of our homework. It's an enormous hole in the ground. It was produced by an asteroid colliding with the Earth. And first thing we want to understand is, why does an asteroid produce such a large explosion? Okay. We also have meteors that explode in the atmosphere. Some years back, there was a really dramatic one over Russia somewhere. And you guys should actually look that up as well. Let me go ahead and put these up as things for us to check out and get pictures of and so forth. So we want to study the Arizona Meteor Crater. And the meteor over Russia. There are many, I forget the year now, you guys look that up, YouTube, etc. Because what the situation is in Russia, apparently people have a lot of dashboard cameras, and so many videos were made of this meteor blazing across the sky and then exploding in a gigantic flash. Okay. Sent a shock wave across the country that broken windows, and amazing. Okay. So these are two things you want to look up, and I'm going to discuss these and explain them. So the question is, why does a meteor produce a gigantic explosion and maybe make a big crater? This thing's a mile across or so, or half a mile. It's huge. Why doesn't it just fall on the earth like a bowling ball that lands in the dirt? Okay, if you drop a bowling ball in the dirt, you're never going to get a big explosion. Okay, so the question is, why are these events so explosive? Question: why are these events explosive? You can drop a rock from the top of a building, a bowling ball, what have you. You're not going to get a giant explosion. So the answer to that is that the power is the kinetic energy. Remember, we discovered that can be work divided by the time it takes for that object to come to a stop. Okay. I'm going to write that in words. Kinetic energy, time to stop. Now that is just a power expression, right? But what we have with these objects is they have enormous kinetic energy because they're going so fast. Asteroids are really moving fast, and the time to come to a stop is very short. And so we can get estimates for how much energy is released. And if energy, which is the numerator, is released over a really short time, that is what an explosion is. An explosive event is just a lot of energy over a short period of time. Now this is mechanical kinetic energy. We'll learn later in thermal physics how and why it gets converted to heat. But it does. Gets converted to heat. It's just an explosive event. But yeah, so the answer is a very large numerator and a very small denominator. So that's the first thing about converting, kinetic energy to work in a short time. It's a lot of power. Again, remember, if you have a fraction like this, the smaller the denominator is, the larger the overall value. Okay, so it has to do with the short time in which it happens. Okay, now as far as the Arizona meteor crater goes, let's kind of draw a picture of the event. So there's some meteor, some thousands and thousands of years ago, comes zooming down, hits the ground here. Here's the ground. Okay. So it hits the ground, and it ends up excavating. It makes a huge explosive event, and it excavates a large crater. Okay. So let's even put this as this is homework. Images and any data, there are websites and stuff about the Arizona meteor crater. You definitely want an image of this thing, data, size, and mass of the meteor. Size and mass of the meteor. And I'm going to show you guys how the rocket, how the scientists estimate the mass of the meteor, okay, the size and the mass of the meteor. So that's homework. And this meteor over Russia, you may even get some good screen captures and print them out, right? Print out all this stuff, or the best ones you find, so you can put them in your book. And we're gonna, you'll have in your book, and we'll have the explanation of what was going on there as well. Okay, so there's a meteor that came in from who knows where, hit the ground, blasted out a gigantic crater. So we'll figure out how the crater works. I want to say something else about this one. So this Arizona meteor crater. The meteor over Russia, it produced sonic booms and gigantic flashes of light. So it actually may not have even hit the ground, or a lot of the energy was gone on the way down. And why is that? That's because the meteor encounters friction with our atmosphere. That friction is enough to heat things up and cause explosiveness itself. So when we talk about the Arizona meteor crater, we weren't there, we don't know exactly what happened, but we're going to assume that a large chunk made it all the way to the Earth and, you know, blasted open that big crater. But like I said, this is also really interesting, so have a good look at it as well. Okay, so I'm claiming we have enough of a conceptual framework here to get a rough estimate of what happened here with the Arizona meteor crater. And, you know, we'll do our rough estimate. It's going to be pretty rough, but I think it'll match reasonably well what was going on, what the websites will tell you. Okay, so good. We have all this. Yeah. So the way we're going to model this meteor crater, we're going to assume something about the speed. Because we know that orbital speeds are 7,900 meters per second, we're going to give the meteor speed as a rough estimate of 10,000 meters per second. And that's a good estimate because there's a thing called escape velocity, which is greater than the orbital velocity. It's about 11,000 meters per second. Okay. That's going to be good. So by saying that this thing has 10,000 meters per second velocity, then we can give an estimate of its kinetic energy, or an expression for its kinetic energy. And for the meteor, here's what we're going to say. We're going to make the claim that, roughly speaking, the kinetic energy of the meteor is going to equal the work that it takes to dig a big hole in the ground. Okay? So, we're going to assume kinetic energy, KE, of the meteor is roughly equal to, so when I say approximately, very roughly, okay, equal to the work that required to excavate the crater, right, to dig that crater. And we're just going to use our definitions. So kinetic energy of the meteor, it's 1/2, I'll use capital M for mass of the meteor, v squared. You know, and the work to excavate the crater, we're going to say it's a form of mgh, isn't it? It's a form of mass times gravity times height, because that's to lift something. So now it gets interesting. We're going to have that mass be the density, I'm going to use a Greek letter rho, density of Earth, times the volume times g. And for the height that it's excavated, I'm just going to use the radius of a semicircle. You know, let's go ahead and draw on this picture right here. We think of this as a semicircle of radius r, and we had to lift the dirt out at least that much. So density, volume, g, and therefore that h is a radius. Okay, and v, volume of a hemisphere, is 1/2 of 4/3 pi radius cubed. As you remember, I think we had volumes of spheres in our chart earlier on this semester. Density, I'll say something about in a minute. Mass is density times volume. And I'm going to have to make some more assumptions here. So this equation, I'll say I have a half. Density of the asteroid, 4/3 pi radius cubed. So this is for the asteroid, v squared. And on this side here, I'm going to have 1/2, no, density first. Density, volume is 1/2 of my 4/3 pi capital radius cubed. But I had another radius right here, so it's radius to the 4th. Okay, that's looking pretty complicated, but it's going to simplify a lot. Because we don't know how dense the asteroid is, we're just going to assume density of the asteroid is equal to the density of the Earth. Okay. Density of the asteroid is equal to density of the Earth. And then we just have a bunch of cancellations. So when you get an equation that's this complicated, you want to simplify it, and you'll see we've got pi on both sides. We've got a 1/2 on both sides. We've got a 4/3 on both sides. And we assume the densities are the same, so they cancel as well. And now we have a v squared. And you know something is missing here. G. G had to be written in here because that was the gravitational acceleration. Hope I didn't miss anything else. So we're going to solve for lowercase r. Solve for r. That's the radius of our asteroid. And what do we get? R cubed. Everything canceled over here is g r to the 4th over v squared. And then to get the radius of the asteroid, and remember this is a very crude approximation, you would plug in the radius of the crater, so you can find the diameter divided by 2, radius of the crater. And what we're going to take here is, let v equal 10,000 meters per second. And g, is 9.8 meters per second squared. If you want, you can always approximate g with 10 meters per second squared. Good. So I just, this is a little more than you came to see, but I'm going to label this enough so that it's something that makes sense in your notes. And then we'll discuss again just the concept of it, because I just put this here together. Let me make sure. So those are densities. That's the volume of the hemisphere. There's g. There's an extra power of r. So the right side is just work, lifting something up, and the left side is the kinetic energy of the asteroid, of the meteor. Okay, so this is reasonably well explained, and if you're ambitious, you can just look up r equals radius of the crater, and you have to convert it to meters. If they tell you miles, whatever, you have to convert it to meters. In meters, okay, G has 9.8 meters per second squared. You can also use 10. And V is 10,000 meters per second. And then when you get this answer, you have to take the cube root, okay? So the last thing, R is the radius of the asteroid, of the meteor, whatever we're going to call it, meteor. This is going to be a very rough estimate, but before you did this calculation, you had no way to estimate it at all. Good, so for that reason, this is a nice topic. And conceptually, this board here has everything you really need to know, okay? But this here is more of a technical discussion. You can have it in your notes as well. And if you calculate it out, take the cube root and compare to the size that's given that you'll read about up here, and I think you'll be impressed. It's pretty close. Okay, how are we doing time-wise? Okay, this is good. Good, so yeah, clean up this technical discussion here. Everything you need to have is on the board. You can make it a little more linear. I'm going to leave that up and erase this here. So we'll just put here. Yeah. Well, I'm just going to say, calculate this r cubed. Make sure you take the cube root, and then you get a result on this. Okay, I'm going to erase all of this and discuss this a little bit more. Okay, so the next question is, here we go. The next question is this: what is the time? What is the time in this asteroid collision? And I'll give a quick estimate for that. What is the time t in the asteroid collision? Can't make up my mind. Is it an asteroid or is it a meteor collision? So that's the first thing. And that's easy to answer. You know, roughly speaking, the depth, roughly speaking, we have distance goes as velocity times time, right? Velocity is distance over time. So we can say t goes like distance over speed. And what we can do is we can plug in the depth of the crater divided by the speed. Now, if the depth of the crater is, say, 1 kilometer, okay, say it's 1,000 meters deep, this is just an estimate. These are all estimates, okay? So let's put an approximate sign. And the speed is 10,000 meters per second. Then all of that gigantic kinetic energy was converted into explosiveness in 1/10 of a second or less, okay? 1/10 of a second. So this is a titanic event, and it just happens very rapidly. That's why it's so explosive. And you just got that from the depth of the crater divided by the speed, just from this definition here. Okay, what else? How much kinetic energy? So that's the first question. This is my last question. How much kinetic energy per kilogram does the asteroid have? And that's anything, anything that falls to Earth is going to have this 10,000 meters per second if it came in from a great distance. It's called the escape speed. So how much kinetic energy per kilogram does the asteroid have? Question mark. Well, this is pretty easy. And by the way, a kilogram is a chunk of metal this big. So imagine you had an asteroid the size of a house. Okay. It'd be quite a few kilograms. Okay. So 1/2 mv squared. That's 1/2 1 kilogram 10,000 meters per second. And let's use our scientific notation. 10 to the 4 meters per second to quantity squared. So that's 1/2 times 10 to the 8. Okay. So that equals 1/2 times 10 to the 8 joules, or 5 times 10 to the 7 joules. That's the energy per kilogram. Now, eventually we're going to relate this to thermal physics, but I'll use red for thermal physics. In thermal physics, we're going to learn, we'll learn it systematically, but I'm going to bring it into play right here. So in thermal physics, we have um, 4,186 joules per kilocalorie. I'm just going to get per kilocalorie times 10 calories per gram times 1,000 grams per kilogram. So I don't memorize these numbers, the results, so I can build it up out of this. This is going to be approximately 4 times 10 to the 1, 2, 3, 4, 5, 6, 7. So what this number represents in thermal physics is the energy of explosive, or the energy of fuel. Okay. So these are joules. You can see they're very comparable. So something coming out from outer space has as much explosive energy as its mass as an explosive. So imagine a bomb the size of a house, okay? Pure explosive the size of a house. If your meteor is the size of a house, that's how much explosive power it has. Let me go ahead and put this in words so that we can hold on to that. And I'll just point arrows at it. This one here, that's energy released by 1 kilogram of explosive. Energy released by 1 kilogram of explosive. I wrote it as calories and stuff because that's how I have it stored away. And these are approximations, but they're very good ones. And this here was, of course, energy released by 1 kilogram of asteroid. Some mass that falls away from, falls onto the Earth from a great, great distance. It's going to release this much energy. So that's another way of pointing out why these events are so explosive. And you know, that's why if an asteroid the size of, the size of a city block hit Earth or something, then it's a gargantuan damaging thing, kills all the dinosaurs and everybody else around. That's the idea. You got to study that elsewhere. But yeah, so we were able to tie in energy, work, power, kinetic energy, asteroid collisions, because we studied orbits, because we studied motion. So now we have a very broad understanding of energy already. It's going to get deeper. Our next big topic is going to be about energy conservation, and then I'll go into the topic of hydropower. But I think for now we're going to call it a day. This is a good place to stop. Once again, your homework was to look up and get images from the Arizona meteor crater and data if they have them there, and the Russian meteor explosion, screen captures, whatever you can find. Good, see you guys next time.